Okay, so what I want to cover now is section 1.3, Predicates and Quantifiers. And if you are in the 6th edition book, then your suggested homework exercises are 5, 9, and 35. And if you're in the 7th edition book, it's the same numbers, but it's going to be section 1.4 problems same problems, 5, 9, and 35. Okay, so if you're in the 6th edition book, which is the book the bookstore would have had, it's that. And if you're in the 7th edition book, it's same problem numbers, just a different section. Okay, so the big things we're going to talk about in this section are the Universal Quantifier, which is an upside down A, the Existential Quantifier, which is a backwards E. We'll talk about the Uniqueness Quantifier, which is an exclamation point, so that's not the same as the factorial, which you may have seen. Uses the same symbol, but in a different way. We'll also talk about counterexamples and Demorgan Negation. Now you might say, wait, didn't we just talk about De Morgan's laws in the last section? And the answer is yes. And this is another type of use of De Morgan's laws. So first thing that I want to do is introduce, I might say P of X, and this is going to be a statement depending on X. So you can think of this as like a Boolean function. You know, it's a function that takes whatever input and it outputs true or false. So let's do a quick example. Okay, so let's let P of X be the statement. So here I'll define it to be X is an even number. Okay, so P of 1 is going to be false. P of 2 is going to be true. And then P of apple will also be false. Okay, so I'm not specifying what the input has to be here. I'm just saying that's what we do with the input. All right, so we're going to use this to make our examples and our constructions just a little bit simpler. So the Universal Quantifier which is the upside down A, is used to discuss any or all elements of a given collection. So an example, and we'll be using these symbols in conjunction with some other symbols soon, but let's go back with the same statement P of X. I could say for all X bigger than 3 P of X. Okay, and this is me saying this is just English, or the English of this is for all X bigger than 3. Oh, I wrote out bigger than. I was going to do a greater than sign. Whatever. Bigger than 3, X is an even number. Now, it just so happens that this happens to be false. Okay. I know if the first number you check is 4, you're like, oh man, wow, maybe this is true, but no, 5, it's false. So this happens to be false, but this is just an example of, you know, a sentence where we're using the universal quantifier. So a counterexample is a member of an indicated collection that shows a universal statement to be false. So from our last example, 5 was a counterexample. Okay, so in this one, this happens to be false because 5 is bigger than 3, but 5 is not even. All right, so that's a counterexample. So now on to the existential quantifier. So the existential quantifier is used to posit the existence of something. So posit is a word for claim or put. I mean, I think it literally means put, but we'd say it puts something like it's putting it on the table for discussion. The existential quantifier, so on its own, it looks like this, or it can be used to posit, now that I said the word, I got it stuck in my head, the existence of something unique and that would be backwards E exclamation point. Okay, so let's do a different P of x here. Let's suppose that P of x now stands for, so whatever it was before, I'm doing colon equals, I'm clearing it out. P of x is now equal to x is prime and x is even. Okay, so P of x is saying x is prime and x is even. We haven't formally discussed prime numbers yet, but hopefully you've got some primitive recollection of what a prime number is. So I claim that there exists a unique x so that x is prime and even. Okay, this I could say way more quickly by just saying, so this is equivalent to, there exists a unique x such that P of x. Okay, so I just said this whole sentence here, I said it right there. Now, of course, that's provided we know what P of x means. Of course, there is a unique x, and this x equals 2. 2 is even, and 2 is prime. All right. You don't have to use the uniqueness operator to use the existential quantifier. I could just say, quick example, I could just say there exists an x such that P of x, and this just claims that there is such an x. When I put the exclamation point in there, this says not only is there an x, but it's also unique. That is, it's the only x that does this. We won't do a whole lot with that, but it's worth seeing, especially because you can confuse that with the factorial, because it's the same symbol used for factorial. So the last thing I want to do is Theorem 2, which is again Demorgan. You didn't know, you thought this was discrete math, not Demorgan class. So this is what I'll call Demorgan negation. So Demorgan negation is going to be a lot like the Demorgan laws, but it's using these existential and universal quantifiers. So not, remember that's the negation operator, not existential quantifier x colon for such that P of x, and this is for any conditional statement P of x, so any P of x, not just the ones that I've been using. I claim this is logically equivalent to, for all x, comma, not P of x. All right. The second one is the negation of the claim that the universal x, p of x, is equivalent to the existence claim of an x such that not p of x. All right, and this thing here should be reminiscent of the counterexample. What this is saying is, if you make a universal claim, I can negate that claim by showing you that there exists an x that makes that, hitherto universal claim false. Okay, so let's prove these. You might want to take just a second and flip back to, or I guess I could flip back to the Demorgan laws from before. So here's what the previous Demorgan laws looked like. So this is a negation. The negation of one kind of operation is equal to the other kind of operation of the negations. The negation of one kind of claim is equal to the other kind of claim of the negation. Okay, so hopefully you can see at least some resemblance. Now I know, like, superficially they look very different, but the more you play with these objects, the more sense it will make. All right, so let's prove number one. So we're going to do this by just by English, kind of like we did with the previous one. So LHS, as you recall, stands for left-hand side. Okay, so left-hand side in English says it is not the case that there exists an x for which p of x. Okay, so just by writing p of x, that's claiming p of x. Right? So it is not the case that there exists an x for which p of x, or for which p of x is true. So this is the same as saying, so if and only if, this is basically saying, so if it is not the case that there exists an x that works, that's saying that no x works, which is saying for every x, not p of x. So we just said there isn't, we just said up here, it is not the case that there exists an x for which p of x. So it is not the case that there exists an x that makes p of x true. Well, that's the same as saying for every x, p of x is false. For every x, p of x is false. Oh, hey, that's what we have written up here. This is the right-hand side. Okay, and that's part one. Now, if that made sense, great. If that didn't make sense, you might want to watch it over again. But you also might want to just watch me explain part two and hope that that in watching part two, it'll make part one make a little bit more sense. So part two, let's do the left-hand side. Left-hand side is saying it is not the case that for all x, p of x. Okay, so we're saying that it is not the case, negating, for all x, p of x, or p of x is true. Right, but that's the same as saying, so if I tell you it's not the case that for every x this is true, that's the same as saying there's some x, a counterexample, for which not p of x. There's some x for which p of x is false. But this, you'll notice, is exactly the same thing as the right-hand side. And we are now done with our proof. When you're done with the proof, you get to draw a little rectangle and then fill that rectangle in. That's your reward for finishing a proof. Okay,